In this video, we're going to be solving Leetcode question 130, which is surrounded regions. Let's get started. So in this question, we're given a 2D array where each element in the array is either an X or an O. And there's a little bit of terminology I have to explain before getting into the correct of this question. There's three terms that they describe in the Leetcode question. One is connection, which is the concept of two squares being right next to each other. Two squares are defined as connected if you can move up, down, left, or right on the grid to get from one square to the other. So for example, this O is connected to this O because you can go from this O to this O by taking one left step. But this X and the O are not connected because that would be a diagonal step instead of a directly vertical or horizontal step. Then there's this idea of regions, which is basically a set of cells that contain the value O in which they're all connected to each other. So for example, this group of three right here would be a region because this one is connected to this one and this cell is connected to this cell. And this is also a region over here, even though there's only one cell in it. And last is the idea of being surrounded. So a region is surrounded where all the cells directly connected to that region are X's. So this region would be surrounded because if you go in any direction, you're always going to bump into an X rather than another O. But this small region over here is not surrounded because if you go down, you don't meet an X, you just meet empty space. So our goal in this question is to identify all the surrounded regions and then replace them with X's. So what's that going to look like on this 2D array is this is the only surrounded region. So in the final array, all of those values are converted to X. But this region isn't surrounded, so that remains an O. All right, so this is the key insight that's needed to solve this question. If a region is surrounded, that means none of its squares are on the border of the grid. I'm going to explain that right now. So first, let's imagine that we have a region that does have a square that's on the grid, on the border of the grid. For example, this little region here. Well, obviously that region can't be surrounded because whichever square is on the border can at most be bordered by three X's. The fourth side of it has to be empty because it's on the border of the square. For instance, if we take a look at this circle, this O right here, it's on the bottom edge of the square. So that means below it is empty space. There can't be an X below it because it's already on the bottom row. And now let's take a look at a region which doesn't have any squares on the border, like this region of 3 right here. Well, because none of these cells are on the border, we can go make a ring around the cells like this. And none of these values can be an O themselves, because if they were, we would extend the region to make that included as part of the region. So it wouldn't be a region of 3, it would instead be a region of 4. So since we know that all of these surrounding cells are X's and every side is surrounded because none of the cells are on the border, then this region must be surrounded. And that means we would have to remove these values and make them X's instead of O's. So now all we need to do to find all of the regions that are surrounded by X's is to just find all the regions that don't have a O on the border of the grid. So we can do that in reverse. First, we could find O's on the border of the grid, and then we could do a search to find all the O's connected to that O, and then all those O's are part of regions which are not surrounded. And then every other O besides the ones we found through the search needs to be replaced with an X. So first in our algorithm, what we're going to do is we're going to search the border and find all the possible O's. And in this case, we only have one, which would be here. And then from any of the O's we find, we need to do a search to find all the connected O's next to it, because these O's are also safe. They're connected to a O, which is on the border of the grid, so it's not part of a surrounded region. So we look in the upward direction, rightward, leftward, and downward, and we don't find any O's. So that means this is just a region of 1. And since that's the only O on the border that we found, that means all the other O's in our grid have to be part of surrounded regions. So we can safely remove all of them. We would keep this O and any other O's we find in some sort of set. So it could be like a set that keeps track of the coordinates for each of the safe O's. And then we just go through the entire array one more time, like left to right, we check if each individual value is an X or an O. And if it is O, we further check whether it's in our already seen list, which means it's fine. But if it's not on our seen list, we have to remove it. So that means we remove these, we replace them with X's, and we keep going, and we replace this with an X2. Once we get over to this cell over here, it is an O, but we also saw it earlier in our search. So that means this one is safe. But then these are not X's. So therefore, the ending array is going to look like that, where all of the O's are replaced with X's besides the one on the border. This algorithm has reduced a fairly complex problem into a simple searching problem. And there are two algorithms we can use to search for O's that are connected to the O's we find on the grid's border. And those two algorithms will be breadth first search and depth first search. There isn't going to be a huge difference between these two implementations, and they are both going to be the same time complexity and space complexity. But I'm going to be presenting a breadth first search solution today. Both of these searching systems are going to take O of m times n time complexity and O of m times n space complexity. And the reason why is because for time complexity, we're not going to be checking any cell more than once. So therefore, the time complexity is just going to be scaling with the total number of cells in our grid. If the grid has a length of m and a width of n, the total number of cells is going to be m times n. And similarly for the space complexity, in a worst case scenario, which would be all of the cells in the grid are O's, we would have to keep track of all of those cells because we need to make sure we don't remove them. So that would also be O of m times n, because in the worst case scenario, it's going to scale with the total number of cells we find in the grid. So now that we know the general idea of how to solve this question, we can code it up. If you're finding these videos helpful, I think you'll love what we got going on in our private community. We dive even deeper with exclusive content that won't be shared on the main YouTube channel. I also offer individualized coding interview study plans that are tailored just for you. You can also join small group sessions, participate in mock interviews, and get your questions answered in live weekly Q&As. It's a great way to take your coding interview prep to the next level. If you're interested, check the link in the description below. I'll see you inside. All right, so this is the Python code for solving Leetcode question 130, which is surrounded regions. First, what I did was I searched the border of the grid to find any cells that have a value of O. So we searched the top row like this, and then the bottom row, left column, and right column. And whenever I find an O, I'm going to save it in the set, which is called seen O's. So these are all the O's that are either directly on the border or are reachable from the border by taking left, right, up, or down steps. And all of these O's are going to be safe. So we keep track of this so that when we go through the grid one more time, we don't accidentally change the value of any of these O's. And I am saving the coordinates of the O. So I will add a tuple where the first element of the tuple is going to be the X index, and the second element is going to be the Y index. Then I implemented this search from function. And what this does basically is it takes in a pair of coordinates, which are always going to be on the border of the grid. And it's just going to check up, down, left, and right to find any other O's that are right next to the original square. And it's going to continue doing this until it runs out of O's to find. Whatever O's it finds, it's going to again add it to the same seen O's set. So after I search the top row, bottom row, left column, and right column to find those border O's, I'm also going to start a search from one of those O's, and then that will get all of the neighboring O's that are part of the same region. And after doing all of that, I found all of the O's that are either on the border or directly connected to an O, which is on the border. So these are all the O's that are safe and we don't want to remove. So then last, all I have to do is go do a nested loop to go through the total array twice. And basically for every cell, if it is an O and it's also not in our seen set, that means it is part of it's part of a region which is surrounded. So that means we have to convert its value from O to X, which is what we do here. And then I just printed the scene O right here just to check that everything's working properly, but we don't actually return anything here. We are supposed to do everything in place. So it passes the test cases just fine. And if we submit it, it does pretty well. 95% percentile runtime and 51st percentile memory. So this is the optimal solution right here.